Hello everyone, this is Dilip. In episode 22, we have seen how to evaluate the hypothesis with some diagnostics. So this video is a continuation to it, and we will talk about variance and bias and how we can determine which way our algorithms are going and how to mitigate the issues that come with them. So we have seen about all these in the video about diagnostics on this. So whenever our hypothesis fails or our backpropagation algorithm is not working or anything in linear regression or logistic regression, any issue we face, then we will come to these conclusions like what might be wrong. And we can go with either gut feeling or we can plot some minimal curves and then go with whatever the output we get after our plotting of data. This we've already seen where given our data for a linear regression problem, this is just an example. If size of the house determines the price of the house, then given a size, if we have to determine price of the house, that's a linear regression problem. Then we divide the data set into 3 sets. So trying, cross-validation, test data set, so that it should not have any bias. And once we try the data, we can use the cross-validation set to verify the accuracy, and then we can use the test data as well. So this way, our hypothesis will be more robust. So let's look at high bias versus high variance. So how to determine whether we have high bias or high variance in our hypothesis. So whenever we implement the algorithm and when we get the result, okay. So with the increase in training samples, if the train error keeps on going up, okay, so it stays at some point. And the cross-validation error, initially it will be high, and with the increase in training samples, it decreases, and it will be nearly equal to the train error. Okay. So when cross-validation error as well as train error, they both become nearly equal, then we are suffering from a high bias problem. So even if you increase the number of training samples, there won't be any good result. So you will continue to have high bias. Okay. Now, how to look at high variance? So high variance in the sense, it's simply overfitting. So whatever the samples we have, the hypothesis will try to fit it in such a way that all the samples, the cost will be very low. So the train error will be like, it will see the initially and then it will keep going down. The cross-validation error, this will keep, it will look like it is decreasing, but it will go up. So there will be a lot of gap between the train error and cross-validation error. If this happens, then we can be sure that we are suffering from high variance. With the increase in training samples, since the hypothesis will not be able to fit it well by reducing the cost as much as possible, with the increase in training samples, we can reduce the variance. Okay. So let's look at all the points we discussed in the earlier part of the video, like earlier video, and then see how to balance out this bias versus variance problem. So as I was talked about in previous slide, more training data fixes high variance. So if you have high bias and if you try to increase the training data, it won't be of any good use. Use more features fixes high bias. Say for example, if algorithm is tilting towards a particular set or a particular class, and if you use more features, it will remove that bias. And if you have a lot of features and it is causing the overfitting problem, then using the less features fixes high variance problem. And say for example, you have a straight line hypothesis. Okay. So a straight line hypothesis may fit some set of data, but if you take more data, straight line may not fit very well. In that case, if you go for higher order polynomial like a quadratic or cubic, then you will get a different type of curve that fits your data well, and that will remove the bias. So going for higher order polynomial will fix high bias problem. And same way, reducing the polynomial will fix high variance. So you might have, with a very higher order polynomial, you might have your curves like this. So it will try to fit all the given data. So your curve might look like this. And in cross validation, it will like fall bad like anything. So to fix this high variance problem, reduce the order of the polynomial. Now, this is the regulation parameter. So if you use a bigger regulation parameter, it will fix the high variance. And if you use a smaller regulation parameter, it will fix the high bias. So thanks everyone for watching the video. Bye.